Hello there, Mr. Sutton here with the AB Calculus 2-6 Extra Practice number 6 solutions on continuity. On this problem, we're trying to find an A and a B value, well actually in this case just an A value, that makes this function continuous. So in order to do this, we're basically going to try to prove continuity, and we're going to leave A around until kind of the bitter end. So if we were trying to prove that this already was continuous, we would find the left and the right side limit to establish that the limit exists. So we need the left side limit at x equals 2, and for that we're going to use the x less than 2 rule. So finding the left side limit at 2 here, that's going to be 2 squared plus 2 plus a, which is going to be 4 plus 2, so that's 6 plus a. Now for the right side limit, which also happens to equal the function value here, so we're getting both of those for the price of 1. That's going to be a times 2 cubed minus 2 squared, so that's 8a minus 4. And in order for this thing to be continuous, the limit has to exist. So 6 plus a and 8a minus 4 have to equal each other. Left has to equal right. And all of that has to equal the function value, which also happens to be 8a minus 4. So basically we have to do 6 plus a equals 8a minus 4. Those things have to all equal each other. So subtracting here, we've got negative 7a on the left and negative 10 on the right side. Or you could do 7a on the right, 10 on the left. Either way, dividing by 7, we get a equals 10 over 7. On this one, we're defining f as this piecewise function, and we want to know what value of b, where b is some mystery constant, makes this function continuous at the border value 3. All right, well, in order for this to be continuous, we need the limit to exist, the function value to exist, and those two things to equal each other. So let's start with the limit piece of this. The left side limit of this thing as we approach 3, that's going to use this before 3 rule. So we're going to have e to the b times 3, or e to the 3b. And then we also need the right side limit at 3, see what that is. That's going to use this greater than 3 rule. So we're going to have 2/3 of 3 plus b. Well, 2/3 of 3 is just 2, so this is just 2 plus b. The function value also factors in as well, but the function value happens to be the same as the left side limit because of this less than or equal to part here. So function value is also e to the 3b. So to show that the limit exists, that means that the left and the right limit have to equal each other. So we can say e to the 3b equals 2 plus b, and now we have to actually use the calculator to solve this for b. So here I am on the calculator. In my y equals, I've entered the left half of the equation as y1, the right half is y2, and of course I'm going to use x instead of b because x is what my calculator recognizes as my input variable. I have to figure out what window to graph this on also. So taking a look at the answer choices, it looks like we could go as far back for intersections as negative 4.5, and the biggest positive, the most positive x value is about 0.394. So let's say between negative 5 and positive 1, that should do the job. So let me go to window. X min will say negative 5, x max positive 1, and now zoom 0, zoom fit. Let's see what those two functions are doing. All right, so here's the exponential, and here's the other function. And although we can't see it very well, we know the exponential does exist as far back as you want to go. There's just a horizontal asymptote as you move to the left with these exponential functions. So somewhere in here, we're intersecting this line. To find out where, let's do second trace, option 5 for intersect. And then my spider's already pretty close to where those are crossing, so let me just press enter 1, 2, 3 times. Gives me an intersection of about negative 1.9975 or 998, I guess, if you round off. So there's my graph. There's my first intersection. And now I need the other intersection as well. We're clearly crossing a second time over here. So second trace, option 5, intersect. Move my little spider over there. There we go. Enter, enter, enter. And that's about 0.274. So looking at my answer choices, that's going to be, let's see here, choice D. And if you are thinking, well, wait a sec, this only covers the limit existing, what about the function value? Well, the function value is also going to have these values, so it's going to exist. And as well, the function value equals the limits because the function value is basically tied in with the formula for one of your limits. So we've got continuity covered by setting this equation up and solving it. For this problem, we're defining g as this piecewise function, and k is a constant that we don't know right away. We want to know what value of k we need to use for g to be continuous at x equals -2. Okay, well, a good way to start this is to basically start a continuity proof, which means we have to find the limit at -2, the function value, and then make sure that those two things equal each other. So for finding the limit at -2, we're asking what is this graph doing as I get really, really close to -2, but I'm not exactly equal to -2. To get really, really close to -2, we need to use all the x values that do not equal -2, or at least we need to use the rule that has those types of x values. Using the rule at exactly -2 will not tell us the limit. So we're actually ironically using this first rule, and if you just plug -2 into this first rule, you're going to have 4 minus 4, which is 0, over -8 plus 8, which is also 0, which is a whole bunch of no good. So in order to deal with that, we're going to have to factor and simplify this function in order to take the limit. So I can split my numerator up into x plus 2 and x minus 2. So I'm doing limit as x approaches -2, and this is going to be a two-sided limit because this function is going to handle coming from the left and the right at the same time here. So I've got x plus 2, x minus 2 in the numerator, and then in the denominator I can factor out a 4, leaving me with x plus 2 down there. And we see that these x plus 2's, that's what was causing us to get 0 over 0 when we just plugged in -2 directly. So if I cancel those out now I can actually evaluate the limit and get something that's not indeterminate. Plugging -2 in at this point, we have -4 over 4, which comes out to a limit of -1. All right, so that was the limit at -2. Now we have to look at the function value at -2. That would be f of -2, or g of -2 actually in this case. Different function. I'm used to using f. Whatever. That equals whatever I get when I use this x equals -2 rule, and that's the constant k. It always gives you k no matter what you plug in. But you're only allowed to plug in -2 for this particular function. So that equals k. Now we know that the limit of g as x approaches -2 and g of -2 itself need to equal each other for this to be continuous at x equals -2. Therefore, -1 must equal k, or k equals -1, giving us our answer of choice B. For this problem, I'm given the function f, and I want to know which statement about continuity is true. So these are all talking about being continuous at 3 or not continuous, and what type of not continuous are we. So let's test continuity at x equals 3. To start this off, we have to talk about the limit as x approaches 3. Now, to approach 3, you have to be, ironically, using the interval of x not equal to 3. Because this rule with x equals 3, you're not approaching 3 at this point, you're at 3. And limits are all about what you're doing as you get close to the number, not necessarily what you do when you get to the number. It's the journey, not the destination with limits. So to find limit as x approaches 3, we need to actually plug 3 into this not equal to 3 rule. When we do that, just doing it mentally, we get 0 in the denominator, which is already bad news. How about the numerator, though? So we've got 2 times, this would be 2 times 9 is 18. This would be minus 15, that's 3. 3 minus 3 is also 0. So we're getting 0 over 0. That means we have some kind of discontinuity going on there. But what type of discontinuity? Well, you might know that 0 over 0 means we have a removable discontinuity, but if you didn't pick up on that little piece, we can keep going here. So in order to actually find the limit, we need to factor this thing. Now, since I'm getting 0 over 0, I know I have a factor of x minus 3 in the numerator. And it's just a matter of seeing what the other factor is going to be. And I know I have this x minus 3 up here because when I plug in 3, I'm getting 0 over 0. So there has to be an x minus 3 up here. Now, if x minus 3 is one of my factors, to get this original quadratic up here, the x has to get multiplied by a 2x. The -3 has to get multiplied by a positive 1 to get this -3. So we should end up with 2x plus 1. And if you just do it quickly, multiply it out, you'll see we get x times 1 is 1x, negative 3 times 2x is negative 6x, adds up to negative 5x. All right, so let's cancel out those x minus 3's. We're taking limit as x approaches 3 of 2x plus 1. At this point, we can just plug 3 in. So that's going to be, let's see, 2 times 3 plus 1, that's 6 plus 1, so that's 7. Now, we also have to look at the function value. So the limit exists. Let's look at the function value. So f of 3 is just going to equal 9, because that's what we do in this rule when x equals 3. So the limit exists. F of 3 equals 9, so the function value exists. The key here, though, is recognizing that 7 and 9 are not the same number. The limit and the function value do not match up. That means we are not continuous because we have a removable discontinuity. If you're going to one place from both sides and all of a sudden when you get there you're somewhere else, that's just a little hole. It's like a piece of asphalt lying on the side of a road because there's a pothole in the road. So that ends up being choice B. On this problem, we're trying to figure out a c value that makes this piecewise function continuous at x equals 3. So we'll start this one by basically trying to prove that this is continuous. And to do that, we have to verify that the limit exists, the function value exists, and that the limit and the function value equal each other. Let's start with the limit. So let's do the left side limit at 3, see what that comes out to. We're going to be using the x less than 3 rule. So 2c plus c sine of 3 pi over 2. Well, 3 pi over 2 is really negative 1, so this is really 2c minus c, which we could simplify to just simply 1c. Okay, now moving on to the right side limit at 3, we're using the x greater than 3 rule, approaching 3 from the right side with these x values. So that's going to be 2c plus 5 times 3, so that's going to be 2c plus 15. And we know that these two things have to equal each other, so let's set them equal to see what value makes the limit exist. So if I subtract c from this side and then subtract 15 to the other side, we get c equals negative 15. Okay, so now that's the value that makes our limit exist. But that doesn't tell us anything about continuity until we connect it to the function value. So let's figure out f of 3 itself. We've done the limit from the left and the right. The actual function value at 3, so and our limit here is negative 15. Let's just verify that. The actual function value at 3 is going to be 7, because that's the rule we use if x is exactly 3. Now, there's an issue here. The two-sided limit that we just found that was negative 15 and the function value, which is 7, don't equal each other. So that means that this is actually not continuous for the c value we just picked. Since there are no other c values that would have made our limit exist, that means that there is no c at all that makes this function continuous, so we have to pick choice D. On this problem, we have this big piecewise function with this mystery k constant. Our job is to figure out the value of k that makes this thing continuous. And the only thing they're going to tell us is that k is positive. Other than that, we don't know. So if I'm trying to make a k value that makes this thing continuous, let me start by trying to prove continuity for this thing, and I'll just keep k around, because we don't know what it is, until I'm able to actually solve for it. So for continuity, we need the limit to exist. So we need to look at the left and the right-sided limits. Left side limit as x approaches 3. We're going to be using the less than 3 rule for that. So plugging 3 in up here, we just get k cubed plus 3, and can't really simplify that anymore because we don't know what k is. Now for the right-sided limit at 3, we're using the greater than 3 rule. So we'll have 16 over k squared minus 3. And we also have to talk about the function value, so while we're on this topic, note that because of the equals here, this limit and f of 3 are really the same thing. So this is going to stand in for both of these values. Now for the limit to exist, the two limits have to equal each other. K cubed plus 3 and 16 over k squared minus 3 have to equal each other. And all of this also has to equal the function value. But we've already got the function value kind of roped in with this 16 over k squared minus 3. So if we solve this for a k value, it's not only going to prove that the limit exists, but also that the limit and the function value match each other, and of course that the function value exists. So let's go do this on the calculator. So I'm going to put each half of this equation as a y equals, so y1 and y2, and I'm just going to see where these two lines intersect, and that'll solve the equation for me. So I need to know what window I'm looking in. Looking at my answer choices here, we've got as far to the left as 2, as far to the right as maybe like 9 if we round up, and maybe there's just no such value. But if it does exist, it's going to be somewhere between 2 and 9. Okay, well, let me just do a window from, let me just do 0 to 10. We'll start there. Zoom fit. Let's see what that gives us. So there's one function, and there's the other function, and not a whole lot going on with that other function. There's definitely some asymptotic action happening there. Obviously, the intersection is happening closer to the 2 area than over here near like 8.5. So I'm going to readjust my window just so I can get a better look. I'm going to make this from 0 to 3 and zoom fit again. I'm allowed to change my window, right? Of course. Okay. So there we go. And the intersection, it looks like, is happening over on this side. It's a little hard to tell. Let me maybe just do zoom one more time. So let me make my window from 2 to 3. Zoom fit one last time. So there's the first function, second function, and here's our intersection that we're looking for. So let me do second trace, option 5, intersect, and I can clearly see where this intersection is now. So enter, enter, enter near there, comes out to about 2.081. And that's going to be choice A. For this problem, we're given this f function, and we want to know on which of these open intervals here is f continuous. Well, probably the easiest way to do this is to figure out where f is not continuous and then use process of elimination. So taking a look here, we've got a few discontinuities. If you look down in the denominator and figure out what's going to zero out each of these factors, we see that we're going to have does not exist happening at x equals plus and minus radical 3 if you set this x squared minus 3 equal to 0 and solve it. So plus or minus root 3 is an issue because of this first factor. And also x equals negative 0.5 is an issue because of that second factor. And as far as I can see, those are our only discontinuities on this. There's really nothing else. There's no undefined areas or jumps or anything like that. Or if there was some kind of jump, it would be at plus or minus radical 3 because of this absolute value. So these are our discontinuities, whatever types they are, one way or another. So let's just go through these intervals now and pick the interval that doesn't have any of these numbers in it. So taking a look at choice A, negative 2 to negative 1, well, that's going to have a negative radical 3 in it. Negative radical 3 is somewhere between negative 1 and negative 2. So choice A can be eliminated. Now choice B, between negative 1 and 0, well, that contains this negative 0.5, so that's no good. Choice C, 0 to 1, that does not seem to contain any of these, so C is still pretty good looking. D, 1 to 2, that contains positive radical 3, so D is out. So by process of elimination, choice C is the only one not containing a discontinuity, so it's the only continuous interval. Choice C. On this problem, we're told that the function f is continuous on the interval negative 2 to 5, not including negative 2 and 5, and is not continuous on the interval from negative 2 to 5, including those two values. Which of the following could not be an expression for f of x? So the key here is that if we're guaranteed to not be continuous on this closed interval, that means that there's at least one value, at least one x value on this interval that has a discontinuity. Now we know that it has to be either negative 2 or 5 because they told us we were continuous from all the values from negative 2 to 5, not including those values. So everything in between is accounted for as continuous. It's just negative 2 and 5 that have the issues. So we're basically looking for discontinuities at negative 2 or 5. If your function has one of these types of discontinuities, then we could be talking about your function when we list out this continuity interval. Looking at our answer choices then, choice A, we have a discontinuity at x equals 5 because of that denominator. So that means that this could be the expression we're talking about that has that discontinuity. So we're not going to pick it because we're looking for the one of these that can't possibly have this interval. So then choice B, we have an infinite discontinuity if you look here at -2. Well, that also could be the function that we're talking about here, so we can't pick choice B. Choice C, that is continuous everywhere because it's a polynomial, continuous for all x. So C could not be this function because this function has discontinuities. So C is looking like a pretty good answer. Just quickly looking at choice D, that has discontinuities at -2 and 5, both of them infinite discontinuities. So choice D can't be it. So then choice C is the only one that can't be continuous on this interval but not continuous on this other interval. For this problem, we want to know where on the graph of f do we have a jump discontinuity. So looking through all these, we have a jump at x equals 1. At 3, we have a removable. We have an infinite discontinuity at 5. So the only one that makes sense then is choice A, x equals 1. For this one, we're given a graph of f, and we want to know on which of the intervals here is f continuous. Probably the easiest way to do this is figure out where f is not continuous and then eliminate intervals that contain those discontinuities. So going from left to right here, we notice that we have a vertical asymptote, an infinite discontinuity at, I guess this is about 0.5, somewhere between 0 and 1 anyway. We'll call it 1/2. This infinite discontinuity is going to rule out answer choice A from -1 to +1. Definitely not continuous if you have an asymptote in the middle of it. But none of the others get ruled out for that. Moving along then, at about 3/2 or 1.5-ish, we have a removable discontinuity. So that's going to rule out choice B, the intervals 1 to 2. Moving along, we have a jump at 5/2. That's going to rule out the interval from 2 to 3. So by process of elimination, the only one that works from 3 to 5 doesn't look like there's any gaps or breaks in that part of the graph, so choice D it is. For this problem, we want to know which function is continuous at x equals 3. So yeah, we got to test all of these for continuity. Let's start with the first one. So let me try out the limit as x approaches 3. To get that limit, I have to use the rule for x not equal to 3. If you're trying to approach 3 from the left and the right, you're basically going to have to use values of x that are not 3. So before I can do this, though, if you plug 3 in right away to this function, you get 9 minus 3, which is 6, minus another 6 is 0. 3 minus 3 is 0 down there. We get 0 over 0. That's telling us we can factor this thing. So two things that multiply to -6 and add up to -1, that would be +2 and -3. And then those x minus 3's cancel. So limit as x approaches 3 of just x plus 2 gives us a limit of 5. Okay, now we need the function value as well. F of 3 is going to be 8. And that's an issue because the limit and the function value don't match up. That tells us that f is not continuous at x equals 3, and we got to keep going. Moving on to choice B here. Now you could check out the limit as x approaches 3 on this one, and you'll get 5 versus whatever you get when you plug 3 in here. When you plug 3 in here, you actually also get 5. So that's great. The trouble, though, is that when you go to do f, or actually in this case g of 3, there's no rule for what to do when x equals exactly 3. We have less than 3, we have greater than 3, we don't have equals 3 like all these other things do. So because g of 3 then does not exist, for that reason, the limit, or the continuity does not exist. G is not continuous at x equals 3. Moving on to h. Left side limit on this one, we're going to be plugging 3 into this less than 3 rule, so sine of 3 pi over 2, which is going to be -1. And the right side limit at 3, now we're plugging 3 into this rule. This is going to be cosine of 3 pi, which is also -1. Function value, f, or actually in this case h of 3, is going to be -1. So the function value and the limit for h x approaching 3, those all match up. So h then is continuous at x equals 3. And you could pick that answer choice, or if you wanted to, you could just quickly check out choice D. So we've got left side limit on this one. As you plug in 3, we're going to have 5 plus ln of 1, which is just 0, so 5 plus 0 is 5. Right side limit, you've got 5 ln of 1 again, so that's going to be 0. This case, the limit doesn't even exist for k, so that would also rule out continuity for the k function. So at the end of the day, it is choice C. On this problem, we're told that f is continuous on the interval from -1 to 3 and not continuous on the interval from -1 less than or equal to x less than or equal to 3. So it's the difference between an open and a closed interval. So which of these following could not be an expression for f of x? So we need to find something that has a discontinuity at either -1 or +3. So taking a look at our possibilities here, choice A has a discontinuity at x equals 3, an infinite discontinuity. So choice A could be the function that they're talking about. Choice B has a discontinuity at -1, x equals -1, so that could also be this function that's not continuous on the closed interval from -1 to +3. Choice C is a polynomial, which is continuous everywhere, so there is no way that we can claim this is not continuous on the interval from 1 to 3, because it's continuous everywhere. So it's going to include x equals -1 and x equals 3 in that umbrella of continuity. Continuity everywhere means it's probably going to be choice C that we're looking for. But let's just take a look at choice D. Well, this one has asymptotes at -1 and 3. So this is kind of the poster child for the conditions they laid out here. The only one then that can't be missing continuity at -1 and or 3 is our polynomial choice C.